Hey everyone, this is Sina with another episode of Into the Bytecode. My guest today is Jim Posen, the co-founder and CTO of Irreducible. So Jim is a close friend and someone who I really admire. And this was a conversation I wanted to have for some time to get an intuition for the work that they're doing to accelerate cryptographic proofs, to kind of like build on the revolution that's been happening with applied cryptography and zero knowledge proofs to build this larger verifiable internet. And so we talk about the work they've been doing with Binius as a proof system that uses binary fields instead of prime fields. We talk about how they're designing new chips, how they're running a data center to make this available to other people, and also how all of this is going to roll out and weave itself into the world in a way that more developers and users can interact with. So I hope you enjoy. Okay, so as a first question, I think we met while you were at Coinbase working on, you had done a bunch of stuff before that, but at the time you were working on open source Bitcoin, Lightning Network, doing a bunch of really interesting protocol development work. And after that, you kind of like took a step back and decided to go do a grad degree in cryptography at Stanford.
Right.
And I'm curious maybe to go to the early days and like the root motivation of like what got you excited about this whole direction and like problem space. Like why did you decide to go deeper on cryptography in particular?
Going deeper on cryptography came about from just going deeper on the protocols themselves. So when I started at Coinbase, I didn't know that much about Bitcoin. I was excited to learn about it, and I was not doing stuff that was particularly Bitcoin related. I was like working on compliance engineering. And then I would say the arc of my time at Coinbase was just going deeper and deeper and like kind of closer to what's actually happening in the blockchain. So when we met and I was working on basically contributing to protocol development and Bitcoin and open source stuff, I was looking at the frontier of kind of where protocol design was going, how you were going to scale these systems, how you were going to add privacy. And I, kept trying to read these papers that involved cool cryptographic ideas. Like around this time, this was confidential transactions were out in Bitcoin. Monero had been around. I definitely didn't understand how Monero worked in that time frame. Zcash was, I think, had been deployed in 2016 or so. And then you also had these papers on verifiable delay functions and threshold signatures. And so I was seeing all this stuff happen. I was trying to read these papers. I think I'm strong at math, but just hadn't studied math in undergrad or anything, like didn't have the language to understand what they were talking about. And that made me want to go and like spend time in grad school or just in an environment where I could focus all my attention on that and like talk with other smart people who were doing the same thing.
And how would you describe like the moment we were in and we're still kind of in? Because I feel like, looking at where we are with technology, there's certain things that are just obvious that we're going through these crazy inflection points, like let's say with AI right now. But I feel like a similar thing has been happening with cryptography, with zero knowledge stuff. And like, so what was it like how would you describe the moment we're in right now?
The moment we're in right now is really exciting, but comparing it to then, I mean, you're an engineer. You've probably heard the like, don't roll your own crypto phrase. Like that was mantra for anyone who was a software engineer or a computer scientist. It's like cryptography is this magical forbidden field where the experts come up with the cryptographic primitives, and if you attempt it, you're going to fuck up something. Yeah, like don't roll your own crypto was this warning that like if you even attempt it, you were going to mess up something subtle and you were going to deploy some insecure code and it was going to be a disaster. And so cryptography had sort of partitioned into like applied cryptography, which was like AES and TLS, and then academic cryptography, where you had all these magical ideas like threshold signatures and ring signatures and zk snarks for arbitrary computation. And so starting, around that time, there was, especially basically prompted by needs of the blockchain space, uh, engineers entering and trying to like implement these protocols and doing it with modern engineering practices and modern languages. Um, and so I think now we've gotten to the point, this is probably 6 or 8 years later, where you have a much more engineering based way of approaching some of the theoretical protocol, like the theoretical cryptographic primitives. Um, and it's also a lot easier to understand them for that reason. So not only is there more writing that's not in the language that academics would use, but the systems and like the frameworks themselves have just been modularized in a way that I think it's a lot more accessible for more people to come in and try to build and drive this stuff forward.
So the fact that there is more of an engineering like lens on the space has made the protocols themselves more, architected in a cleaner, more modular way, in a more legible way.
Yeah. And I mean, maybe this is jumping ahead, but the work that we're doing on binary fields it basically arose because I work with hardware engineers, or Irreducible has a hardware engineering team. And as a result of conversations with them and them explaining the hardware benefits of binary fields, which is, a digital logic engineering problem, that goes and informs what we want to do on the theory side.
I mean, yeah. So how did that come about? Because you're kind of you're like a singular data point of how the research and the implementation have kind of like evolved hand in hand, right? In the case of Binius.
Binius is, I think, a fairly unique project right now, but there have been a number of projects and people who I look up to who I think like really exemplify this cryptographic engineering, software theory, co-design type of stuff. I mean, starting with Zcash and like the work that Sean Bowe and Dara Hopwood and them did over there, they came up with all these really amazing cryptography ideas without as much sort of formal training, just from looking at the needs of like how they're going to get better performance. I also, I basically started at the company that's now Irreducible, originally called Ulvatana, shortly after Plonky 2 came out. And Plonky 2 was, again, it was not written by anyone who had a cryptography degree. It was, built on the observations about what CPUs were really good at and what CPUs could do efficiently, which was 64-bit math instead of 256-bit math. And they managed to get really good performance out of doing that. With the binary field stuff, it's interesting where the project started because we were trying to implement all these different protocols at Ulvatana, at Irreducible, that other people had designed, and these were prime fields, arithmetic, and elliptic curve stuff. And we realized two things. One, hardware was not great, or like custom hardware wasn't getting as a huge benefit over GPUs. And also, it was clear that like none of these were permanent. There were always new prime numbers to be found. And there's something about, when you looked at all these protocols, like, is this actually the way it's going to be implemented in 2 years? And it's like, no, it's headed in the right direction, or like there's more work to be done. So because hardware development cycles are so long, we wanted to make sure that we were like building the right thing and not wasting our effort. So I was doing a lot of research into these new types of snark systems that were field agnostic, meaning they didn't have as many requirements on the fields that you were using. And so that, opened the possibility of using binary fields, which I knew about vaguely. And the other interesting thing about binary fields is that were they did appear in a lot of earlier Snark literature. So the original ZK Stark paper and the Fry paper that the Starks are built on used binary fields. And then we were looking at this, and it sort of just seemed like everyone dropped them and no one talked about it. And it was like a bit of a mystery. Like what did these people realize that made binary fields impractical? So we kind of explored it from that angle of just like solving this mystery of like why in practice are these not as efficient? Um, and what we started to realize was there were some reasons that you might not have wanted to use binary fields in 2018 that didn't apply anymore in 2023. And so, and then we had to, kind of push a little harder and find some new ideas to really make the benefits shine. But that's how that work kind of came about.
So you kind of had this in like this lens of, okay, we know there have been a bunch of cryptographic breakthroughs. We want to like bring this into the world in a way that it can have an impact, and that and to do that with hardware, you have, because the development cycles are so long, you need to have more of a first principles, long-term like thesis about the thing to design for. And if all of this is like changing and evolving on these short-term timescales, like where is it all going? And that kind of led to the insight of, well, hardware more natively handles binary logic. And there was this previous generation of cryptographic protocols that used binary fields. And let's go look into this. And then you found that some of the assumptions underneath that had changed over the intervening years. And it might make sense to bet on that seriously.
Exactly right. One other thing that happened here is, well, this was sort of floating around in my head. I mentioned it to the hardware engineers. Some of them like had prior familiarity with binary fields, and some of them, all I needed to say was, instead of addition, you're doing XORs, and they were just, they lit up. They were like, "Oh, you make this work, Jim," or like, we gotta be doing this. So that was sort of the extra motivation to go and try to solve some of the issues that prevented them from being immediately useful.
Yeah. I guess maybe before going into my next question was going to be what changed about why binary fields were kind of left behind for some period of time, and it makes sense to focus on them now. But maybe before we go there, to ground, to like motivate why this even matters. Why is this a project worth taking on, and all the complexity that it involves? Like, where does it get us if this works?
It gets us potentially huge performance improvements, which is what the industry needs. I think performance of snarks is really the thing holding back adoption. There are a number of things that we need to solve, but ultimately, if you have better performance, you can make trade-offs that enable better developer experience, and you can simplify protocols to get better security. And when you get the cost and time to produce a proof, another 10 or 100 times lower, and it becomes a no-brainer to start using this, I think we'll see just an immediate upgrade in the security that all protocols have by default. I think of this as sort of like there was a moment probably in the early 2010s when most of the internet was not using HTTPS. It was just over unsecure HTTP, and people in a coffee shop could sniff your internet traffic and like see what you were browsing on the internet. And HTTPS was used for like select pages, logins. I remember the website I was working on at the time didn't want to pay the like extra few $100s a month for a HTTPS certificate because they didn't get it. And now everything uses HTTPS, and it's because it became so much cheaper to do it. There was not a penalty you were paying in bandwidth or latency or cost or any of that. And so the whole internet just gets a security upgrade. And I think the same thing will happen when snarks get cheap enough. So that's that's why we care about performance and why Irreducible is tackling this problem at all. And then to answer the question of like, why is kind of Binius an important project to go after? We think that this is the best approach to unlocking the benefits of custom hardware. Like when we've done some experiments that compare resource utilization or basically compare the efficiency of doing binary field arithmetic to uh, prime field arithmetic, which is more conventional, and basically looking at the efficiency. If you were to go and make a custom ASIC, this is around a 5 to 7 times efficiency gain, taking into account clock speed and total silicon area. So that's sort of what's available here if we chase this down.
What is the analog to the internet leveling up to use HTTPS? Like, I've heard you kind of frame the mission of Irreducible in a way as building the verifiable internet, right? What does that mean? What does that look like in practice once we're living in that world?
What it means is right now, like a lot of the information you get on the internet, either you don't trust and you need to like do more, do more vetting yourself, or you just trust a few sources of information for um, providing content and providing security. And I think as we're moving into a world where more decisions are being made automatically and we're relying more on AI for, telling us what to do. And we are, trusting images that may have been AI generated or videos that are AI generated. And the idea of the verifiable internet is that everyone will have a digital identity and you will have powerful primitives to authenticate the sources and the sources of information that you're seeing. So, this is, and things that are more powerful than just Jim signed the message to you. Maybe I want to hide my identity. And so, that, someone at Irreducible or someone who has a certain history on the blockchain made this type of claim, there's a idea of kind of image provenance where you have an originally authenticated source of data, but then you want to do some transformation on it, like just put a black and white filter on a photo, and you then want to carry the chain of trust forward after that computation. That's what verifiable computing lets you do. And I think it is a little far out as a notion right now, but just the idea that most of the information that you're seeing, you can have much more powerful ways of knowing, where it originated from and who's authenticated it.
Yeah, totally. It's because we don't usually kind of touch and feel it in our everyday experience. It feels like a foreign concept, but it's almost like it's like a huge missing kind of primitive in the internet once you think about it, right? Of right now, basically any like transformation, which is like basically anything that happens on any server anywhere, you kind of like trust the output of that when it's served to you on your client. And here we're talking about a world where there's cryptographic receipts attached to everything, that this computation actually happened the way you were told it happened. And I feel like the kind of like blockchain native use cases where all of this stuff is first getting deployed, like building rollups that use validity proofs, or building bridges that have light clients underneath them that use validity or use state proofs. This is kind of like a special case of that problem where you can think of a blockchain as a piece of state that has a transformation happen to it in certain in like an iterative structure, and it's just and we're basically using zk proofs to show that transformation happened correctly. But the same idea can be applied to any computation, and this is it's not coupled to the notion of a blockchain in any way at all.
Right. And I think, one thing I've struggled with this framing is most people don't understand like actually what the word computation means and how it encapsulates like so much of your digital interactions. Like if you're looking at an Instagram feed, you're probably not like thinking about computation, but like there's a whole crazy algorithm that's going on behind the scenes to decide, you know, what to show you in that moment. And that's a ton of computation, and that's like ultimately the type of thing that we're talking about authenticating when this becomes really cheap.
Right. Like the Twitter or the X feed algorithm is open source, but we don't actually know that it's the one being exactly used when I go to x.com.
Right. You're trusting X.com to be using the algorithm they say they're going to use. And if you want to start to decentralize that system, prerequisite to that is being able to not have to trust the provider and the information for the accuracy or um, the validity of it.
Yeah. There's also a deeper thing where like the web will become, or the internet will become more interoperable in a way, because right now the only way you can get data and kind of, use it in some way and, output something else is the whole thing is structured with these like HTTP client server like calls. But here we're talking about a world where each like piece of data has a cryptographic like kind of like authenticity stamp attached to it. And so you'd no longer need to make these calls to get the data from a server. Like you can just pass around the piece of data on its own. You can store it anywhere that you want. So I feel like it will have like pretty big ramifications in the architecture of the internet and like the types of applications that we can build, like how much permissionless innovation there can be, because the notion of like kind of like gatekeeping the data that a service has and like only like giving it to developers via a specific API, all of those sorts of things change when users are like getting these cryptographically signed like data packets and like can pass them around in different ways.
Yeah, absolutely. Like, I mean, the thing, one of the reasons I got into blockchains and Bitcoin originally was I had an appreciation of how powerful peer-to-peer protocols were. And this ultimately goes back to that, which is we have an architecture of the internet that's very kind of built around centralized hubs. And a lot of that's because we need some amount of trust in the internet infrastructure in order to make it work at all. And if you try to design peer-to-peer protocols that could deliver you content, faster because it's being served from someone closer to you or anything like that, you just pretty much immediately run into this issue of like, how do I trust whoever my peer is that they're giving me the right thing or they're telling me the right thing. And that's why blockchains kind of are positioned to make peer-to-peer protocols more powerful, because blockchains are fundamentally platforms for verifiable computing with shared data. But now if you have cryptographic verifiable computing, which doesn't require consensus in every way, you can start to design peer-to-peer protocols that disintermediate these trust hubs on the internet. And yeah, I think it could really change the architecture of how we you know transmit information digitally.
Yeah. And another thing which like improving the performance of these proof systems will do is it's not only like the end user experience or like these services like using it in their workflows, it's also the developer experience, right? Of like right now to build a product or a protocol that uses these cryptographic primitives in any way, you have to like wait for the proof generation and the verification, and like your feedback loop just sucks, right? And if this whole thing is happening faster, like it'll that it's like an amplifier on how on if if and how these things can even be used in applications, right? Like the process of like building something where you're like feedback loop, like if your test suite or like if you're trying to run something locally, it takes like 5 minutes every time to like go through, is maddening. And it's really hard to like get traction with something like that.
Yeah. Developer experience is paramount. I mean, just when you look at from web frameworks, when you had easier to use web frameworks, the number of new like feature rich websites that sprung up, after you had like the LAMP stack and Ruby on Rails and stuff. Like the same thing is happening with CK, and I think companies like RiskZero and Succinct, who are building these general purpose VMs that let you run arbitrary Rust code, are going a long way towards expanding the field of people who can use this, expanding the base of developers who can integrate verifiable computing into their protocols. And then it becomes just a matter of cost and performance to, for people to actually want to adopt it.
Into the Bytecode is sponsored by Splits. Are you tired of sacrificing security for usability? Splits believes it's still way too hard for teams to self-custody their on-chain assets. They're building a new kind of internet-native bank on top of Ethereum. Splits makes it easy for teams to manage the whole lifecycle of their finances, from structuring revenue sharing agreements, using payment flows like splits and waterfalls, to managing those earnings once you receive them, using passkeys and smart accounts. Splits is being used by teams like Protocol Guild, Zora, Songcamp, and others. I'm a big believer in them and recommend checking them out. You can learn more at splits.org. Okay, so maybe going back to where we were, you got this sense that binary fields are something to bet on. And the hardware engineers you were working with got excited about XORs instead of additions. So if we like try to get into what Binius is and how it works, again, for like a somewhat technical audience they're not cryptographers, they're like, 1 degree removed from all of this. I guess maybe as a first entry point, why were binary fields being used early on and then were like put aside? And how did you get the sense that you could use them as a part of the design now?
So why they were used early on is because they're already used throughout cryptography that you use like every day. Binary fields are used in AES, which is the advanced encryption standard. They're used in QR codes for the error correcting codes used in QR codes. So cryptographers have known about binary fields because they have, good hardware acceleration properties, and because they just map a lot better to digital systems, which are what computers are, than prime fields or other mathematical objects do. So that's one of the reasons that cryptographers, were initially.
And why, maybe to ask a dumb question, why do they map better to digital systems? Like what about hardware is binary more native to?
Well, so all digital systems are built out of bits. Like you have a bunch of wires, pieces of silicon that are either high energy or low energy, or high voltage or low voltage, and so you're propagating bits around. And a binary field is mapped perfectly to a certain number of bits, right? So the binary field that AES uses is exactly 1 byte. So you can take a byte of data and encode it 1-to-1 with an 8-bit binary field element, and then go and encrypt that, and you've now encrypted a bunch of bytes. Whereas if you tried to build this out of any field, any finite field that was not a binary field, you would have a mismatch in like the amount of information. So to get into like what prime fields are, these are integers modulo some prime number. So if we picked like 7 as our prime number, and you look at, you can have 7 different values, and you tried to put that into a certain number of bits, you would have to pick 3 bits, which gives you a maximum of 8, and then you're sort of missing there's one value you like can't use out of those 3 bits. So there's just the fact that it's binary, and we have digital systems that are binary. In some sense, it's as simple as that. There's other benefits, which is that when you try to add these things, it's an XOR operation, and XOR is bitwise independent, right? It's like, an XOR on a bit is the same as doing an XOR on a string of 8 bits. It's just completely
So
independent.
you don't need to do this extra move of like keeping the carry and like moving it over. Like the whole thing is much simpler.
That's right. And the carry, both is just more gates that you need, but it's also propagation delay, meaning in order to compute the output of an integer addition, you need to sort of wait for the result from all of the previous bits pretty much to figure out the result of the final bit. Whereas if you have XOR, it's pretty immediate because
like
everything's
parallelized.
independent. It's parallelized. Yeah. So that's why binary fields are efficient to implement in hardware, and why they just sort of match up better with, what hardware is capable of doing.
Yeah, so AES and these other things were always using binary fields. And the early SNARK stuff was using binary fields. So then what happened?
And there's one other reason, which is, I think if you ask some of the authors on the Fry paper and the ZK Stark paper, binary fields are very elegant. There's a lot of kind of edge cases that you need to deal with prime fields that do not appear in binary fields. They just have a certain mathematical elegance that draws, theoreticians to like them. And for good reason, because I think just, I care a lot about this, but you sort of, when you work on math and theory and engineering long enough, you get the understanding that elegance is like it's an intuition for something that's actually good. Like, you maybe not know exactly how it's going to be useful, but if something's really elegant, it's going to pay off by using this. That's a bit fluffy, but I do think it's true. And so it's the combination.
I think that's like a pretty deep thing. I feel like it's, I guess it's rooted in this intuition that the laws of physics almost can't have like weird special cases. They need to, they are simple there, and that's the direction that I feel like all of knowledge has tended in, right? It's like we realize simpler rules that kind of describe all these like higher order effects. So if there's something like something feels elegant or fundamental to binary fields, even if we don't know exactly how to get there, there's an intuition that it's a worthwhile direction.
Absolutely, yeah. I mean, to point out one concrete thing about binary fields, and when you're trying to do error correcting codes over them, in prime fields, you have the amount of encoding you can do does not go up to the size of the field. So if you have a 32-bit prime field, for example, the one that RISC-0, the baby bear field that RISC-0 and Succinct use right now, you can only encode up to, I think, 2 to the 27 symbols, even though you have 2 to the 31-ish field elements. Whereas with a 32-bit binary field, you can encode up to a length of 2 to the 32. There's no gap. It's just, it lines up perfectly. So that's like one of these places where the elegance of binary fields just kind of shows up. So yeah, the early Snark and Stark works. The early Stark works and works on hash-based Snarks. We're using binary fields, and then this was really driven by Starkware at the time in terms of engineering. Like, they were the ones implementing Starks. They invented Starks, and they put out a system called ETH-Stark, which was commissioned by the Ethereum Foundation, and it used prime fields. And frankly, I think if you ask a lot of practitioners like how they came to understand Starks and how they worked, they'll probably refer more to the ETH-Stark system than to some of the theoretical works. And so after that point, maybe I just, don't have the full insider view, but like when I was looking at this, it just sort of seemed like, oh, people stopped doing binary fields when they went and tried to build these into practical systems. Like what gives? And there are some various subtleties that, like, binary fields are kind of weird. There are certain things you can't do with them that are easier to do with prime fields, especially given the zk Stark architecture and the rest of how that protocol worked. There were certain things that were easier with prime fields. I'd say the other one is people were building this stuff in software and they were running them on commodity CPUs and GPUs, which have basically have native integer multiplication instructions. On a computer, doing a 32-bit integer add is not any more expensive than a 32-bit XOR. It's only when you drop to the level of building custom hardware accelerators that you can see this, potential 5 or 7x speed up. And so the things that I think changed when we were looking at this again in 2013 were 2023. When we were looking at this again in 2023, there was a new architecture for designing snarks based on multilinear polynomial math and the sum check protocol, and this was kind of pioneered by some of Justin Thaler's work and the Spartan protocol by Srinath and Hyperplonk, and there are a number of papers using multilinears, which is a very different type of technique. It's actually an earlier technique than the types of techniques that Starks were built on, and they were getting like a resurgence in practical usage. And that overcame a lot of the limitations of why you might not have wanted to use binary fields in the first place. And the second thing that I think really contributed was there was another re-architecture of snarks where the way you expressed computations was relying much more heavily on lookup arguments. So previously, the original snark programming model was called an arithmetic circuit. You would have like a circuit of that, into prime field additions or finite field additions and finite field multiplications, and everything had to boil down to, an addition or a multiplication. And a lookup argument lets you program much more arbitrary logic that sort of fits within a certain size, and it lets you design circuits that are much more field agnostic. When you're using a lookup heavy architecture, you tend to not care as much about how your field multiplication behaves. What a lookup argument is, it's a lookup table. So you just have, a fixed amount of input. You have, 16 bits of input, and you interpret it as like, give me the multiplication of the first 8 bits with the second 8 bits, and it gives you an output, and you just do a lookup into this thing. So when we were looking at snark architectures again in a world where lookups were really prevalent and where we could use multilinear provers, we were able to overcome some of the challenges that people had run into with binary fields a few years earlier.
Interesting. So there was a degree of pragmatism and path dependency when this started, where it was first applied in the Ethereum context with ETH-Stark, and you're running the code on CPUs anyway, where the optimizations are not as relevant, and there's also this element of this has, at that point, taken this step from the world of theory into the world of engineering. And we have this first implementation, and the kind of engineering community starts to shape around it and move with the momentum of that. And you make a lot of progress doing that, but you've kind of, you're on this branch of the tech tree that isn't rooted, that hasn't really like updated its priors on on like, yeah, we should consider re-architecting how this works under the hood. And then in 2023, with these multilinear provers and the new lookup architecture, it was a right moment in time to take on these extra challenges.
Actually, let me make one other point. So the thing that we really contributed with the Binius paper, one, it was sort of a statement like, hey, let's combine these various ideas. Let's go back to binary fields. Let's combine them with multilinear provers. Let's use lookups to make them practical. But the real like theory contribution was my co-author and I figured out a way to also combine this with the small field movement, which is the idea of you when you're designing a snark, you need a large field for cryptographic security. But there's a lot of the computation that you can do on smaller field elements. And when you work with smaller field elements, it's less memory usage and it's a lot cheaper. When you reduce the size of your field, you get disproportionately large gains to the efficiency of multiplication by doing that. So, and people had been doing this starting with eStark and then Plonky 2 and then RISC-0. We're all moving from like 256-bit fields down to like 64-bit fields and 32-bit fields. But because of some fundamental design decisions with how ZK Starks work, you couldn't go below 32 bits. And so we termed those small fields, and with the Binius work, we figured out how to use tiny fields, which are fields that are below 32 bits. And we wanted to say, how can we get, as much efficiency as possible doing proofs for circuits over 1-bit elements, which we'd known that a lot of other teams were using these 1-bit elements, but they were just treating them as 32-bit elements and paying a 32x performance penalty by doing this. So we said, how can we make use of 1-bit elements without paying that embedding overhead, that performance penalty? And we came up with some cool coding theory ideas on how to encode single bits more efficiently and how to commit them. And then we basically made improvements on that work the following year in 2014, and that's the system we have now. And that's, I think, from a theoretical point of view, the biggest innovation of Binius, and then the subsequent paper that we call Binius.
So, okay, so you that makes sense, and you've kind of like made this progress on the theory side, but this is all only relevant if it can be implemented in practice, right? And that's the hard part. That's why people didn't want to do any of this stuff to begin with, right? So as Irreducible, you're not only doing kind of research and theory work, you're also implementing it. But again, like if given that the whole project is about performance gains, like you need to optimize the entire system, because it's in a way, it's like it's a chain link system. If any part of it sucks, like the performance of the whole thing will suck. So you need to do the software, you need to do the cryptographic engineering, you need to do the software engineering that like wraps that, and you need to actually build the hardware that this thing runs on, because again, if it's running on CPUs, you don't get the performance improvements. So okay, we've talked about like the theoretical kernel of this. How does it like wrap into a production system?
So, first we began when we were doing the research. We basically started coding this. I think we knew we were onto something. We knew this was going to be a project that we pursued, but at the time it was to just sort of get the initial benchmarks on like concretely how much faster could we be if we use these techniques. And we showed, really significant performance gains when you were trying to commit tiny field elements, meaning 1-bit elements and 8-bit elements. And that gave us a lot of conviction to go forward with it. And I think it excited the applied cryptography community that we were onto something as well. So we had the the layer of the stack, which is the open source reference implementation. This has both verifier code and the prover code. Um, and, I think this distinction is important. So a proof system has a verifier that would run on you know, you might be trying to verify proofs that I generate. So yeah, the verifier needs to run anywhere. It's optimized for simplicity. It's optimized for security. It's going to be fast pretty much no matter what because of the nature of succinct succinct proving. And the prover is the one where you want to just squeeze all the performance out of it that you possibly can. So we have open source Rust versions of these things. And then, yeah, we have our hardware team is designing custom hardware accelerators. It's basically a custom computer design. So you send it instructions that say, here's where I want to read from memory, and here are the binary field operations that I want to do. And, they've designed a scalable, highly parallel architecture for doing arbitrary binary field computations. And then we have a systems software stack, which is basically how do you communicate between this high level Rust code that's doing cryptography and this, bespoke new CPU architecture. And actually there's a lot of really interesting challenges there that we've had to solve, ranging from we've written custom drivers for the FPGAs because the default drivers weren't giving us the performance that we wanted. We have a actual compiler for writing, say mid-layer level code that executes the proving algorithms and compiles it to the instruction format that our custom hardware accelerators take in as input. We need to distribute computation across multiple FPGAs that are all in one server. So a server in our data center can have up to 8 FPGA cards attached over different PCIe slots, and so we need to distribute the workload across all of these. So there's some really cool stuff that needs to happen at that layer as well. And then this all needs to kind of work together in and then we have an infrastructure team. We have our own servers in a data center. And the reason we do this, one, there's cost benefits to having your own servers as opposed to using the cloud, but also until recently, AWS or GCP did not support the server configurations that we want. Recently, AWS launched a new instance type just in the past few months called F2 instances that get a lot closer, but basically when you use the most modern hardware and hardware configurations, you can get much better bandwidth transfers than what was available in the public cloud. So these are all the components that we need to pull together to have something that can be optimally performant.
That's freaking intense. There's a lot
It
there.
is, yeah.
So okay. I mean, kind of as someone who's not, who's hearing about this from a distance, it feels like there's a parallel to how AI compute and chip design and server architectures have worked, right? Where NVIDIA had to create, innovate on the GPU. And then there's ways in which these GPUs, similar to how you said the FPGAs, there's 8 of them and they're communicating with each other. The GPUs need to communicate with each other. And a lot of the efficiency gains are actually in that communication overhead. And that's why folks, that's one of the big debates in the decentralized, training and inference world, or the training world primarily, of can you run these interconnects on the internet, or do they need to be co-located in a data center somewhere? So are you kind of doing, in what ways does this analogy hold? You basically have to design net new chips that are optimized for running this kind of binary computation that we're talking about?
Yes, that's fundamentally what we're doing. We're trying to, you know, build something that's like a GPU architecture specifically for verifiable computing. And if you look at what GPUs are optimized for, they're basically trying to pack in the most number of floating point operations per second as you can do. You hear about like flops, floating point operations per second that a GPU is capable of. Uh, for our architecture, we're trying to push through binary field arithmetic. There is something I glossed over here, which is Binius does not use a single binary field. It uses a family of binary fields of different sizes. So in the way that a computer can operate on bytes and 32-bit words and 64-bit words, the Binius system for efficiency tries to use the smallest field size that can accommodate a particular computation. So uh, you can write circuits that use 8-bit elements and 32-bit elements and 64-bit elements and 128-bit elements. And so the CPU design that we have allows you to do vectorized operations on any of these field sizes, the way that works best for the proof system. So we are, building basically a custom instruction programmable chip that's designed for verifiable computing, much like how a GPU is basically a custom designed chip for parallel AI type workloads. And then if you look at the other things that NVIDIA has had to build, which you pointed out, they needed to figure out, multi-device networking. They acquired this company, Mellanox, that allowed them to transfer data, much more efficiently within a data center between machines. We are, as I said, like we have 8 FPGAs working in a single server, and we need to, move data between the cards and the host really efficiently. And I think in the long-term vision, we want to build custom system on chips, which is where you co-locate the CPU processor that's orchestrating the computation with the hardware accelerators on the same piece of silicon. And that's something you're seeing in the AI world as well. And then the other thing that NVIDIA had to build was, and like what really enabled them to make the transition from graphics cards, video cards, to general purpose GPUs, was the CUDA software framework and development tool chain. So they put all of this work before AI and was really a thing into building a software platform for people to write C++ code and run arbitrary computations on this massively parallelized type of hardware. And they wrote, compilers and tool chains for this stuff. And in some sense, that's how we see Binius, which is it's the single target that we know we can build really good hardware for. The difference is CUDA only works with NVIDIA's hardware. That's a strategic decision they made. Whereas in the SNARK space, that doesn't make as much sense. We have a fully open source, really good optimized reference prover and a verifier, and anyone can use Binius with or without our hardware. We just think that we're capable of designing the best hardware that's going to make it run the most efficiently.
That makes sense. And the CUDA analog here is zkVMs or something like that?
It's the Binius proof system, and then on top of that, you could build zkVMs or constraint systems.
Yes, that makes sense. It's the Binius proof system.
Yeah.
So this is kind of a monstrous undertaking. So I'm curious if you think about it in terms of like the stages of development, like if there are, kind of like, I guess it feels wrong to call something like this an MVP, because the MVP is so it includes so many pieces and takes like, I don't know how many smart people like years to build. But like the V1 is the V1 that works end to end, and you can use in a production setting, say to do Ethereum state proofs or to do zkVM stuff. instead of doing the custom chip, you're using FPGAs, right? Because they're programmable. What does like the V1 system, and maybe getting into some of like the raw challenges you're having to deal with to like get this thing off the ground? Like, what's even involved in like running a data center? Like, what does that even mean? Is there like a rack somewhere that you go and like plug these things into, and you have to like figure out that power, supply that they get? Like, what does it take to get this thing off the ground?
Yeah, I'm jealous because our infrastructure engineers have been the ones going into the data center and plugging things in, and I haven't had a chance to travel out there yet. But yeah, we literally have something like 25 servers in a few racks in a data center that's hydroelectric powered, and each of these has 4 to 6 FPGAs in them attached over PCIe, and so we need to manually configure the networking for these, and sometimes you need to kind of update the so you can reprogram the FPGAs remotely, like the user logic for them, but there's a kind of another layer of programming that's more of what I think of we call like a shell, or I think of it as like the operating system for the FPGA that takes more work to go and program.
Why do you have to do that rather than use what's available off the shelf?
We basically ran into bugs and performance issues using the off-the-shelf shell for the FPGAs, and so this was a large endeavor that our hardware team kicked ass on, and basically adapted this open source alternative shell to match our types of workloads. And also kind of simplified the functionality of it. So like the one that's provided by AMD, who makes the FPGAs, has a lot of functionality for kind of every different way that you might want to interact with the FPGA. 2 of them are you can either transfer data in streaming fashion, or you can transfer data as a batch memory copy, which is more similar to how GPUs work. And we only deal with streaming data, so we could kind of write a shell that only had to handle that type of interaction path. But yeah, there were also just essentially bugs we ran into because no one else was publicly talking about having the types of workloads that we have. So FPGAs are, my understanding is they're used in a few places. They're used for prototyping hardware that you actually just want to go and make a chip for, and they're used in academia. And then in production use cases, they're often used in like high frequency trading for very low latency applications. Meaning, you're a trading firm, you're trying to make extremely fast decisions on whether to place an order, or, put something on the order book or whatever, do packet parsing, but they're not designed for high throughput. And our workload is, we don't care as much about latency because we just have so much data, and we're trying to maximize for sustained throughput. So we're trying to basically get 100 plus gigabits per second streaming to the device, full throttle. I mean, full throttle would be like 128, so 100 to 128 gigabits per second to each card. For as long as possible and sustain that. And when you start to like push the limits of that, then yeah, we encounter
it's just
issues.
Not designed for that.
Yeah. I forget what the original question was.
What you've had to do to get this off the ground and working.
Oh yeah. And then as far as like the MVP, just there, as you said, there's a lot of moving parts, and it's been a challenge where like we're making progress on all of them, but then like the hardware is trying to target some version of the proof system that we're accelerating, but then the software team's pushing new versions of the proof system. And like, so we, in the beginning of January, launched what we do think of as like the MVP proof of concept for doing a really, a useful computation, or verifying useful computation with Binius, which is related to Ethereum stateless client verification. And that is a live service that we're running that runs on the servers in our data center. And we were using an early version of the hardware architecture to accelerate them. And as we were getting, closer to the deadline, we got the system completed, and then our software engineers went and made it, like 4 times faster in the span of like a week or two or something. And so the hardware team kind of had to keep up with that and like identify, oh, well, that thing's no longer a bottleneck. So now we need to go and hardware accelerate this other bottleneck. And so, yeah, when you're working on a system where you're doing acceleration for kind of a moving target, you want to be pushing forward as fast as possible on all fronts. And, there's some coordination challenges that come with that.
What a nerd's knife. I can't imagine a more interesting thing to work on. So you have...
And it really is like, I just think the coolest set of problems that I've had the privilege of working on.
Well, also like knowing you in particular, right? Because you also after your cryptography degree, you were doing some hardware hacking when we were hanging out.
That's right. Yeah. So it's exciting for me to get to learn more about hardware, to like learn about, as I said, low-level systems drivers and compilers, and obviously the cryptography engineering aspects of this. And it's a startup, which if you go and work at like an AI accelerator, like you're probably just working on a very small piece of this whole system because it's just such a huge industry. Whereas there's just no one else out there doing binary field snarks and hardware acceleration. And we have sort of everyone in the same company trying to like do that end to end. And so that, there's a lot more fun for me that there's smart and humble people around to just ask questions to about things that I have zero understanding of.
Yeah. Okay. So this is what you're building. This is where it is today. We have a sense of where it's going. We talked about the idea of the verifiable internet, verifiable compute, and like this is the kind of the kind of North Star that this whole thing is oriented towards and enables. But maybe kind of like coming back to the more short term, the more, short to medium term, and like where this stuff is going to be used in the world, right? And 2 things I'm curious to talk about are the Ethereum stateless, proofs, and zkVMs, right? Because that's all happening right now. So maybe... as a sketch of the Ethereum state proofs question, like what is the service that you launched there, and what sort, why does it matter?
So what we launched is a service that follows the Ethereum blockchain. For every block that comes out, we basically do some inspection on what got executed, and in particular, looking at across all of the transactions that happened, all of the contracts executions that happened, what are all the accounts that needed to be read in order to provide input to the smart contract execution engine. And we would take that set of accounts, we would do lookups into the Ethereum state trie for the authentication witness for this, meaning like all of the Merkle data that goes into checking that these account states were valid with respect to the last block. And then we would use Binius to compress these. So, for like an average block, I think it was something like 2 to 3 megabytes of Merkle authentication data. And we could compress that down to, something like 750 kilobytes in the end. For larger ones, it was slightly larger, but it would not grow linearly. The whole point of the snarks is that it's the burst size would grow pretty slowly as you increased the input size. And why is this interesting? Ethereum has this full snarkification roadmap, which is to say Ethereum wants everything that you're reading about the chain state to be fully verified with cryptographic verifiable computing in a few years. And one of the nearer term goals is to allow for stateless clients that don't store the chain state on their own, because that requires a lot of expensive SSD storage. That's probably the main cost for running an Ethereum node today, that you need like a 2 terabyte solid state drive. And instead, you could have a version of running the Ethereum chain called a stateless client, where you're actually fully validating every transaction that happens. But instead of storing the state between transactions, you're getting the database input that you will need to verify it from one of your peers. And in order to make that work, you need the smallest possible witness, or you want to transfer the least amount of data to the client so that they can check this. And we basically showed that Binius, can get meaningful compression on these types of statements. It is, admittedly short of the full what you would need to run a stateless client today, because we were trying to create a proof of concept for this. But that's the service that we launched.
That's really cool. And yeah, it's invaluable to get a system up and running, and then you can iterate on it with the feedback loop of a real use case on the other side.
Yeah, this is a real use case for a complex problem. It also demonstrates that the circuit model, or the constraint system model that we have for programming Binius, which is something new that we designed called M3, we wanted to show that this was powerful enough to prove complex statements like the Merkle-Patricia tri-verification. And I think practitioners who have built other systems we've gotten really good feedback from them that this is an exciting new paradigm for ways to design constraint systems and virtual machines, and very application oriented solutions like the MPT verification system that we launched.
Merkle-Patricia tri.
Right.
Yeah. And you're also doing work on the zkVM side, right? You're working on a project with RISC-0. Maybe, yeah. What is a zkVM, first of all, and what does it mean to have a zkVM use Binius under the hood?
Right. So a zkVM is it's basically a ZK circuit that emulates and verifies the execution of a instruction machine. So, in the basic snark model, you create a circuit that does some computation. We could take the Merkle-Patricia tri verification as like it's a concrete application where the input is just the Merkle data. What a zkVM does is it takes in programmable instructions and the data, and it will run the machine. So what RISC-0 pioneered is the idea of using a standard instruction set called RISC-V, which is supported by all modern compilers, and there's actual CPU chips. And for RISC-V execution, they can compile Rust and C and C++ programs to RISC-V instructions, and then provide those programs and the input data to a ZK snark and validate the execution of this standard architecture, and by proxy your Rust or C++ code. So that's what a zkVM is, and what it would mean for a zkVM to be built on Binius is that you would have a Binius circuit that implements the verification logic of the RISC-V computer architecture. And so the proof that when you're generating and verifying the proof of the RISC-V execution, it's actually using the binary field techniques and the multilinear polynomial techniques that define the Binius system.
Yeah. So basically a developer the zkVM will take all this underlying complexity and abstract it away, where you can basically write code in Rust or C++ and think about how to architect what you're building so that it is using proofs and verifications. And like you have to kind of like think of those primitives. But other than that, all the underlying cryptographic engineering and the math and all of that is abstracted away. And then you get this whole like binary, native, like hardware optimized performance gains out of the box.
Yeah, the end user experience is exactly that. You write a Rust program and you feed it into this system, and it will give you back this small and cheap to verify binary proof. And behind the scenes, it was using this system that enables fast proving and hardware acceleration and everything without you needing to worry about it.
Yeah. So I think soon people will be able to touch and feel this with their own hands and experience Binius.
Yeah. So as you alluded to, we're really excited to have a partnership with RISC-0. They're building the next version of their RISC-V zk architecture on top of Binius. They have an excellent team. They were really very forward thinking in trying to do this, and it's remarkable what they've achieved, and they're fully bought into our vision for this hardware acceleration roadmap for Binius as well. So we're excited to work with them, and we also have a partnership with Polygon to develop a different type of zkVM that has a different set of application. It's sort of geared for a different type of application, but
what's that one?
So that's a partnership we announced last year, and that's sort of more to match their needs, and also hopefully a type of system that can be synergistic with other VMs that like the RISC-0 one.
Yeah, so there will be different kind of like front ends that make different sets of design choices and trade-offs and are optimized for different use cases, but they use Binius under the hood.
Exactly. Yeah.
Well, I feel like we're coming on time. There's so many places where I feel like we could have introspected and ended up into another, hour and a half long conversation. But I'm super happy to have finally jammed together here. Yeah, Jim is one of my close friends and brilliant human being. And yeah, it's inspiring to kind of see you guys take on such a, forward-looking, full stack, ambitious, impactful, technically complicated and challenging project. And it's like we can do pretty amazing things when we put our minds to it. So I'm rooting for you guys.
Thank you. And yeah, it's a pleasure being on and getting to it was a pleasure getting to talk with you. And yeah, thanks, Sina.
All right. Hey, I have a small ask here. If you've been listening to these conversations and want to support what we're doing here, I would really appreciate if you leave a rating and a review for the podcast. It might seem like a small thing, but it actually makes a big difference to help other people discover the show also. Thank you, and I'll see you again soon.